Kia ora koutou, ngā mihi nui ki a koutou katoa, ko Glen Rowe toko ingoa. A very warm welcome to you all. My name is Glen Rowe, and it is my pleasure to introduce the first live presentation in a series of talks for the 2020 RASNZ online conference. If you haven't viewed them already, I would encourage you to check out the talks by Katie Bowman on imaging a black hole and René Breton on pulsars and Einstein's theory of general relativity. But now on to tonight's talks. If you have any questions for our speakers, please use the chat function and we'll put your questions to our speakers at the end. First up, we have Dr. Nick Rattenbury of the University of Auckland, who will introduce us to Te Pūnaha Ātea Auckland Space Institute. Over to you, Nick.
Kia ora, Glenn, thank you very much. Kia ora koutou katoa, ngā mihi nui ki a koutou katoa. Haere mai ki te hui. Thank you very much indeed for being here. It's an exciting time that we are attempting this new form of conference talks in the society, and I hope this is something which we could probably do a little more often to reach a wider audience. It's my pleasure to present to you tonight some of the activities which have been going on in this very odd year at the University of Auckland in the space systems and science engineering research streams. A little bit about myself, just in case you weren't sure. I am a senior lecturer at the Department of Physics at the University of Auckland. I returned back to the country quite some time ago now, about 7 years ago now, from brief 10-year period over in Manchester. I work with MOA collaboration, looking for extrasolar planets via microlensing, and I am, as of the AGM, the immediate past president of the society. I am also a member of Te Pūnaha Ātea, the Auckland Space Institute. This is a new institute at the University of Auckland, and its goal is to develop space science and engineering at the university and make sure that we are making the most of the resources at the institution, plus also more broadly throughout the country, to allow us to generate the next generation of space scientists and engineers, plus also people who are able to service the New Zealand space economy. That goes beyond just the people who work in the engineering labs and the people who work on the scientific projects, but also the people who are capable of understanding how a small society, a small economy like New Zealand could be leveraged most effectively to get the innovations that we make in this country into the international global supply chain. And it's certainly been a fascinating journey over the last few years, where we discovered that there are a number of companies already present in New Zealand which are servicing that global trade chain, getting their technology out there and providing their wares to the likes of NASA, JPL, and others. And part of the remit of Te Pūnaha Ātea is to try and make sure that we provide graduates to that economy and also further afield. We have a director of the Institute. It is Professor Guglielmo Aglietti, formerly of Surrey. Professor Aglietti's research interest is in deployable structures in space, and his crowning achievement to date is the Remove Debris mission. Remove Debris is a satellite which was designed to test various technologies specifically for removing debris, for getting rid of items in space which are things like defunct satellites no longer under any control from Earth, and deorbiting them, bringing them back down to Earth. So as we know, there is a dire problem with space junk, space debris, uncontrolled, uncontrollable pieces of leftover bits and pieces from former space missions, accidents, or otherwise detritus which have been left in orbit, essentially polluting various orbits around the Earth. Professor Aglietti's work has been in trying to figure out how can you best deploy technologies to get rid of that material. I mentioned these two gentlemen here on the left, well, on the far right is Jim Hefke, and in between him and Professor Aglietti is Tristan O'Hanlon. Both of these gentlemen run the Auckland Program for Space Systems. You'll hear more about that later. The Auckland Program for Space Systems is an undergraduate enrichment program started in 2017, wherein we run a competition for students at the University of Auckland to come up with, design, and build a 1U CubeSat and have it flown into low Earth orbit. This program was hugely ambitious. The hypothesis was that we could get a student team completely working on volunteer time, so not for any university credit, to come up with a mission concept to design the satellite, to build the satellite, and fly the satellite within 2 years. So that was our hypothesis. We were able to say that we were not able to hit that timeline, but we certainly learned an awful lot along the way. The enrichment program started off as an internally funded project within the university, but it quickly captured the imagination of external funders, including one philanthropic funder who funded the APSS program so that we could fly not just one satellite, but a fleet of 5. And so the competition continued. We now have the second satellite being constructed. The third satellite is in concept phase. And as of today, we've chosen the 4th satellite, our 4th student team, to design and build their satellite. Should also point out one of the architects of this program, the Auckland Program for Space Systems, is Professor Richard Easter, head of department at Auckland, and he was the initial director of the Auckland Space Institute, and until we were lucky enough to entice Professor Aglietti to come to the country with a team of people to take up the post, and you'll hear more about that in due course, no doubt. We're ably assisted by Catherine Qualtrode, managing our administrative affairs and keeping us on track with numerous projects. My research partner in crime, so to speak, is Dr. John Cater in the Department of Engineering Science at the University of Auckland, and between he and I, we involve ourselves in a number of research projects within the Pūnaha Ātea Space Institute. Another institute at the University of Auckland, which is of relevance to this talk, is Te Awamarama, the Centre for Fundamental Inquiry. This is a research centre, again, set up from initial internal funding, and it is a fundamental questions institute. We try and answer some large questions, the big questions, such as, what is life? And the question has been around for, let us say, millennia. How do you define life? What is it? How would you know it when you came across it? How would you know it if you saw it perhaps in the upper atmosphere of Venus, for instance? How would you know it if you came across it on Mars? And this is more than just a scientific question. This is more than one which is strictly held within the confines of, say, biology, but crosses disciplines into philosophy, amongst other things. And the Centre for Fundamental Inquiry was set up so that we would bring together people from across the university who had expertise right across the spectrum, including the engineers, the scientists, the biologists, mathematicians, computer scientists, people who are interested in artificial intelligence, emergent properties of complex life, for instance, complex systems, plus the philosophers and plus people from Te Ao Māori who are able to give a different perspective on what it is to view a system of life processes as just that. And so the Te Awamarama has been busy. There are a number of people here. The top left is, actually on the top row there is the executive of Te Awamarama. Top left is Professor Kathy Campbell. Kathy Campbell works within the School of Environment and has served on NASA advisory boards, deciding where to send the next rover onto the surface of Mars. Richard East is there again, and Dan Hikaroa works within Māori Studies, the Faculty of Arts, and Emily Park on the top right there works within the School of Philosophy. And then there's a crowd of other people who are working within this group. We don't limit ourselves to the question, what is life? But that is certainly one which has captured our attention. And so we have people like Anne Poole from the School of Biological Sciences. There's myself with interest in finding extrasolar planets and relating the sort of thinking that we have to the surfaces of worlds which we are discovering both in our own solar system and the planets which we're finding elsewhere in our galaxy. We have computer scientists such as Alexei Drummond and Matt Edbert. John Cater's there again, Mike Rowe from the School of Environment, and Peter Wills, who is a biophysicist. And so we answer these sort of questions like, well, there's the research itself founded on hypotheses of how life started here on Earth, such as the warm shallow pool theory, and seeing if are there ways that we can leverage off our understanding of these processes here on Earth to inform missions further afield. When we say further afield, we mean in our own solar system. So I'm taking you through a journey here of thinking, and it's kind of a serendipitous collection of research projects which have come together, which kind of I'm stitching together in a slightly cheeky way to tell you a story about how we could possibly make our way through the solar system and utilize some of the technologies and science that we're studying within the Space Science Institute at Auckland to tackle one of these, one of the biggest questions we've had. What is life, and can we find it elsewhere in our solar system? So we're motivated always by the science. We're motivated by the question, what is life? Where can we find it? How does it exist? In what environments can we speculate that it would exist? And how would we be able to design and build a spacecraft that will be able to go and find evidence for life? This is not a new endeavor, of course. This has been going on since, well, spacecraft have been conceived and successfully launched into orbit and further afield. But what I'd like to do is try and draw you a picture of the sort of research that we're doing and tell the story of how all those research projects can fit together in a coherent whole. So first of all, we've got to get there. And one of the research streams that we're interested in is looking at innovative ways of getting around the solar system using innovative new thrust technologies. One of these is to use not a chemical rocket, but use a ion rocket, one which, instead of being hot material which has been fused together in a chemical process, such as a kerosene and oxygen rocket providing thrust, instead, the stuff which you throw out the back of your spacecraft as propellant are very, very light ions. They're very, very light, but they're moving extraordinarily quickly. So this is work that two of our PhD students are doing at the University of Auckland, Felicien Ferlier on the left there, and Antonella Caldarelli, working with our colleagues at ANU, Christine Charles and Rod Boswell. They're looking at generating plasmas which can be tamed, can be entrained, and can be formed so that they produce effective thrust on a small spacecraft mission. Here's an example of one of these things. This is the pocket rocket that is designed and built by folk at ANU and Stanford. We have one of these at the University of Auckland. But also we are moving into these sorts of systems here. Again, this is a plasma unit where instead of, well, we have a much higher charged plasma, and experiments are continuing by Felicien and Antonella on these sorts of plasmas, looking at how they can be utilized as space thrusters. That image there is from ANU and their laboratory. We have built a copy of this, an improved version, if you will, at Auckland, and we're pleased to report that we are managing to get first light, I suppose you could say, of these plasmas as they spark. This system here on the left, showing you here, is this has all been moved away now because it's been made way for a much larger plasma thrust system. But to give you an idea of the scale, that little device there is the pocket rocket, which is this item up here, spitting out a spray of gas. And this was a very simple, basic style of these sorts of propulsion systems. While we reuse these, well, they have a number of advantages. First of all, you don't need to carry around with you a whole bunch of propellant mass. As opposed to chemical rockets, which most of those systems are mainly propellant. A little bit of news. Earlier this year, a team of people led by Professor Nick Long at the University of Wellington, the Robinson Research Institute, won $11 million for funding research into high magnetic field electric propulsion for space. And this is the next step up. This is looking at how you are able, can you design a system which is able to produce much higher magnetic electric fields in space? Again, all of a sudden it's quite tricky. so that it can utilize these sorts of space plasma propulsion systems. And so John and I are on that bid with our colleagues from the University of Canterbury, Nick Long and his team at Robinson, plus a whole bunch of others. So this is work which is exciting. We're looking at a new form of propulsion and developing the technologies to putter us around the solar system. All right. So you've got a thruster, and let's say it's a good thruster, but it doesn't produce you a lot of so-called delta V. It doesn't give you an awful lot of thrust. It produces a gentle breeze of ions out the back, and so long as you're outside of an intense gravity well, or so long as you're patient, then your thruster will get you around quite effectively, but just it might take a little bit of time. Now, the problem with this is that a lot of the mathematics and algorithms which were developed alongside the early rocketry and spacecraft emissions from the 1960s onwards, they're all predicated on having a massive chemical rocket producing your thrust. With these sorts of low thrust thrusters that we're developing, we have to re-examine that assumption. We have to challenge it. We have to say, well, a lot of the mathematics that we've got and the computer algorithms that we're developing was predicated on having a large amount of delta V, a large amount of thrust at any given time. That is completely not the case with this new class of thrusters. And so we had to go back and take a look at how do you produce trajectories which make sure that you're not being fooled, that assumption is not causing you trouble. Your results are still accurate, given that you're not using a great deal of thrust. Excuse me. So this is work which another PhD student of ours, Darcy Graham, is doing with us in physics within the Institute, looking at how you get from one place to another in environments like the solar system, ensuring that the algorithms do not rely upon the assumption that you have a very powerful rocket. And for instance, we set Darcy the task of, well, can you get from the Earth to Venus with one of these low delta V trajectories? And she's made some good progress with that, and written a paper and had that accepted, which is quite exciting. Darcy is working with colleagues at NASA Goddard Space Flight Center, and that has recently met with success with this paper that she has published at one of the American astronautical conferences, remotely, of course. This brings me to another issue. Of course, this has been a terrible year for students. We'd have very much liked Darcy to have gone across to NASA Goddard Space Flight Center. She had an invitation to go there and work. We would very much like Felician and Antonella, our plasma propulsion students, to be working at ANU for doing some field work over there, but unfortunately COVID has meant that has not been possible, which is a shame. If anybody's interested in seeing Darcy's talk, of course, she was not able to present her talk, her research in America in person, but in the same way that we're doing here, we pivoted to online conference talks, and you can see Darcy's talk there. I can share the link for her talk. I'm not going to play it here. All right, so we have a thruster and we have mathematics which will tell us which way to point that thruster. What do we do? Well, if we're going to get into an environment which requires some atmospheric entry, for instance, the upper atmosphere of Venus, for instance, or indeed managing to land something on the surface of Mars, for instance, or indeed returning a sample of material from orbit to Earth, for example, you need to have some kind of heat shielding. And this is work which is being led by another PhD student of ours, Philip Nyeke, and he is looking at making foam out of titanium. And so instead of just having a block of material, block of titanium in this case, or any other block of material, we're looking at the thermodynamic properties of, instead of a solid block, a simple structure, foams. We're able to now 3D print complicated structures like the foams there on the left of the screen, and we're interested to see if that producing foams with these sort of multiple nodal struts in them have interesting thermal properties which allow us to fine-tune heat shielding. What you're trying to do is minimize mass in the spacecraft, while at the same time having the physical characteristics that you want. In this case, preventing a payload from heating up too much. And so Philip has made some great progress in this. The next step is to take some of these foams that we have, that Philip has optimized for our end use, figuring out how hot it's going to get through given environments, and then taking them off or sending them off to plasma wind tunnels in Germany to expose them to the sort of conditions that would be expected when these materials re-enter an atmosphere. One might say, hey, you guys are already making plasmas with the propulsion stuff. Why don't you use the plasma for that? Flesio and Antonella would lose their minds, because this sort of process here, where we're ablating material off a titanium surface, will absolutely pollute the vacuum chambers and the interior of the experiment. So this is not possible. We'll have to go to a more high energy and appropriate lab space. So this is work which is being funded by MBIE. Okay, so we've got our thruster, we've got the mathematics to get us to where we want to go. We could probably survive a payload getting into the atmosphere or through an atmosphere. What do we do then? Well, now we're going to talk about what sort of experiments you could do, what sort of data you could acquire once you've got your spacecraft in the right environment. And I'd like to highlight some work which has been done by Sarah Kessens at the University of Canterbury. She is funded by a number of places, National Science Challenges and the Catalyst Fund, to look at conducting biological experiments in space, leading to a more complete understanding of life on Earth. But the first part of that statement is what interests us: conducting biological experiments in space and also being able to bring those biological labs back down to Earth. So that's her work, and we're interested in leveraging off her experiences and what she manages to develop for payloads, which could be taken to regions in our solar system to investigate in situ those environments for evidence of life. So Sarah's work is looking at the proof of concept, which is crystallizing proteins in low Earth orbit. But we're able to, Sarah is able to generate or create a lab on a chip, basically, a very small biological experiment which can fly on very modest satellite systems, and we're working with her on producing such a system. All right, well, all of this is predicated on the fact that you can get outside of, or at least out of, much of Earth's gravitational well. Our plasma propulsion system is absolutely not going to be able to do that, so we're going to need a lift. Enter Rocket Lab USA, which naturally everybody, I'm sure in this audience, knows about. They have been cheerfully launching rockets to orbit from the Mahia Peninsula. And they have a kick stage, which is the third stage of their rocket, which very accurately deposits payloads into orbit. And they have ambitions to go further. There on the top right there, you can see the moon. They are very keen to adapt their third stage to be an instrumentation platform, which could head out towards the moon. And it's the bottom left there is their trajectory on proposing that. So getting out of the Earth's gravitational well is ably managed by Rocket Lab USA, which we're delighted. And that is giving us our lift out of the, in this speculative mission, getting us out of this gravitational well. So we have some bits here which add to a grand plan of a mission to Venus's atmosphere. Why would we choose to go there? Well, no doubt many of you will have seen the recent results which reported a detection of phosphine in Venus's atmosphere. The existence of phosphine can be explained by life processes. It's not the only way that that molecule can exist in an environment. However, that captured a great deal of attention, no doubt your own. And so Venus's atmosphere had for quite some time been speculated as being an environment which, certainly in the upper reaches, about 50 to 60 kilometers up, could have the conditions which were not the same as the surface, where it is 470 something degrees and under immense pressure, which is clearly inimical to the sort of life that we enjoy here on Earth. However, further up in the atmosphere, conditions could be, it is speculated, rather more benign, including having liquid water droplets existing and liquid water being the molecule which we consider to be vital for supporting the sort of life processes needed for life to emerge and also sustain itself. So excitement is building for a mission to Venus's atmosphere. This is something which Rocket Lab have picked up on as well. And they are contributing to similar kinds of mission. But we submit that our interests within the University of Auckland and backed up with our colleagues throughout the country, extending from the scientific query, such as represented by Te Ao Marama, the Centre for Fundamental Inquiry, what is life, where do we find it, emboldened by the sort of work which our local experts are doing in biological experiments, which could be conducted in space, enabled by the sort of technologies that we are researching at Te Pūnaha Ātea. It looks like we're getting all the pieces together that we need. We have propulsion within space, we have trajectory analysis, we have entry or re-entry heat shielding technologies enabling us to get a laboratory experiment to do in situ experiments. And this is a sort of a working plan for the going from a definition of life through to a detection experiment, which we build and fly and have delivered to an environment elsewhere in the solar system. But of course, we need to have that lift from Rocket Lab first. But that is kind of drawing you a picture of the sort of research that we're interested in doing currently at the University of Auckland, along with our colleagues throughout the country. I can't leave without mentioning this. So the press release today, we have announced that the first student CubeSat mission will be launched on a Rocket Lab launch, Flight 16. The launch window for Flight 16 opens on the 16th of November in New Zealand time. And this is the first satellite to come out of the Auckland Program for Space Systems, that enrichment program which I mentioned earlier. It was built by University of Auckland students and part of the Auckland Program for Space Systems. It's got a couple of Langmuir probes. Basically, let's try and zoom in on this image here. Okay, so the Langmuir probes are these two knitting needles here. This is the CubeSat. It is 10 centimeters on the side. It's covered with solar panels. Those solar panels will deploy on orbit, exposing other solar panels to provide more data. For those of you who are wondering, yes, there is a great big blue box on your screen. That is because I've had to edit this image. I want you to take a look at the APSS satellite, because the technology which is being looked at here by John Cater and our student Francis Moynihan-Levy, who was part of the APSS-1 team, and the Rocket Lab USA FIT engineer, Carl Campbell on the right-hand side there, that is protected information. And so what I want you to do, and basically it's covering up the dispenser that Rocket Lab has for us, in which our APSS satellite currently resides. So the dispenser on orbit will open up a door and the APSS-1 satellite will pop out. And sometime after that, it will start up its boot up sequence. The burn wires will burn, the solar panels will deploy, the antenna will deploy, and the mission begins. So the Langmuir probes are these two knitting needles here, which will deploy on orbit and will start to make measurements of the upper atmosphere, the ionosphere. And this is a difficult region of Earth's atmosphere to investigate. We know that it is affected by the solar wind, and the team was interested in investigating to what extent the ionospheric disturbances might be correlated with geophysical activity. And so that is pretty much the work that we have been doing this year. Space Systems Research at the University of Auckland, the Auckland Program for Space Systems, and Te Pūnaha Ātea, the Auckland Space Institute, and Te Ao Marama, the Centre for Fundamental Inquiry. Thank you, Glenn.
Well, thank you very much, Nick. It was a fascinating insight into the work being carried out at the Institute and by all those students. Pretty exciting place to be involved in at present, I imagine, and we'll be looking forward to that for very near launch on Rocket Lab, as I guess you folks will as well.
Oh, yes.
So, Steve, have we got any questions in the chat for Nick?
Excellent. Will a future, so the question, I'm just repeating it just in case that we heard it, will a future student project include a telescope and a camera? Okay. The Auckland Program for Space Systems is something which we allow this a bit. I very much want one. I definitely want a. I want to see New Zealand's first space telescope fly, and I'm pushing that. I can't make the students engaged in the Auckland Program for Space Systems do what I want them to do. Their ideas come from themselves. They look at. We have a number of ways that we judge the competition. As people have proposed optical instruments on the spacecraft, and none of those missions have been chosen to win the competition. That's not a consequence of their decision to, or their desire to fly a telescope or an optical system, I should point out. But I certainly would be interested in doing exactly that. And there are a number of missions, one of which I can't really talk about right now, but which will be doing exactly that, flying a telescope on a small satellite for astronomical observations. But nothing yet in the APSS program yet. The next mission, APSS-2, that is going to be flying an electromagnetic tether, which is basically a long wire coming out of the satellite, and looking at to what extent that satellite's orbit can be modified by electric current flowing up and down the wire. Again, this has sort of got a vibe of deorbiting the satellite sooner, to remove it or to investigate how quickly you could intentionally deorbit a satellite at the end of its life. The third mission, APSS-3, will be looking at it'll be an educational satellite. So this is one where we will be working quite closely, I hope, with the team to try and inspire high school students, possibly younger students, into space science and engineering, and the utility of space for scientific endeavor. Yeah, so nothing coming up just yet, but that doesn't stop us from it doesn't stop me from pushing wanting to have a space telescope. A New Zealand Space Telescope is what I want.
Okay, are there any other questions, Steve?
No,
for Nick?
The stream can hear me now, but no, there's no other questions. But if there are any others, then throw them in the chat, and Nick may have some time after the next session if he's hanging around. But yeah, no other questions at this point. Okay,
I'd like to throw one in. If I may, you mentioned, Nick, a number of the students involved in different aspects of the program and everything, but you also mentioned teams of students constructing these various satellites. So how many students are involved in those small teams?
Right. So the competition team, when the teams that submit their final design review, usually around about 5 to 7 students. And I should point out that those teams have to be comprised not just of from one faculty. So they can't just be a team of engineers, and they can't just be a team of scientists. They need to find people throughout the university, other students who have training in, let's say, business studies, commerce, media studies, that sort of thing, because we're trying to replicate in some small fashion what it is to design and build a mission similar to how you would be doing this in a much grander scale, asking for a large amount of money. They have to identify stakeholders, they have to make a business case, they have to make a convincing business case, they have to produce posters, they have to produce media products, a video, and all these things. Let's just say that science and engineers may not be the best people to, direct a video, just trying to present their idea in the best light. So they have to engage with a wide range of people from across the university, other students from across the university, to get their mission sorted out. When such as today, when we've chosen the winner of the 4th APSS final design competition, We could only choose one. We could only choose one winner. Unfortunately, we could only build one satellite. And so that team of 5 to 7 students who wins is very happy, and there's a whole bunch of students who are less happy because they were hoping to win, obviously. But what happens then is the winning team then looks around the body of students who were involved with their own competition, unsuccessful on that occasion, and then ask, all right, we're going to need more people to build this satellite. And so they try and attract more people into their group, saying, you know, your project didn't win. That's unfortunate. Come and work for us, because you can't build one of these satellites with a very, very small team, not successfully, not without a whole bunch of pain. And so those students who were unfortunate on this occasion to win this round are invited to join the larger team and put their skills to work for the team that was successful. And so the team can get quite large. And of course, I should point out again, this is a completely voluntary program. The students are not doing this for credit. They're doing this effectively on their own time. And so there's a reasonable degree of attrition in the student teams as students, you know, realize the commitment which is required for this. Students recognize that, you know, maybe spending more time on this than other parts of their education, trying to juggle everything else, may not be in their best interest. So they, you know, regrettably move out, and we try and get other people to take their place. But, you know, such is the nature of running a team.
All right, thanks, Nick. Okay, we'll move on to our next speaker for this evening's session. So it's my pleasure to introduce Tome Love from Martinborough, who's here to talk to us about how to make useful spectroscopic observations with a small telescope.
Right, sorry, I've just unmuted myself, and can I just check that the screen sharing is working?
Yes.
Great. So, kia ora koutou, thank you, Glenn. So this is, I guess, sharing a bit of a personal discovery. I'm very involved with astronomy in a very active way a long time ago. Nick mentioned the MOA project, and I was involved at the very beginnings of that in 1995. But since then, I've had not much sort of active astronomy at all. So a couple of years ago, I started doing a bit more astronomy, and I've discovered a number of interesting things that I didn't know before. So this is really about sharing some of that. And the first is that spectroscopy with small telescopes is a thing, which it didn't used to be. So I'm going to talk a bit about that and how it works and how that can be done, and share some of the results that are going on that amateurs are doing with small telescopes in terms of doing really interesting science with fairly typical amateur astronomical equipment. And I guess the big message here is those 2 points at the end. There are certainly limitations and challenges to what you can do. You know, you don't have a very large telescope or telescopes with mirrors that are meters across, but there's a lot you can do. It's very feasible, and there is some really good science that you can do with typically available kit. So the thing for those who were new to this, so light is made up of waves most of the time, and when waves are very short, they're blue, and we typically sort of put those on the left-hand side of a plot, as you see here, and when the waves are very long, they're red. We typically look at them on the right-hand side of a plot, and if they're really, really long, then they become radio waves, and if they're really, really short, they're ultraviolet or X-ray waves. So that's the spectrum. Spectroscopy is all about measuring that rainbow. So typically you use a prism or a diffraction grating. A diffraction grating is essentially a mirror with some very fine lines on it to break out the different wavelengths of light, and you take a picture of that. If you've ever seen a CD or a DVD accidentally produce a rainbow of light, then that's essentially a diffraction grating, a very simple one. If you take a picture of that rainbow, then you can essentially measure the brightness of the object you're looking at. It's a whole load of different wavelengths, all the way from the blue to the red, and you can do a graph of that, and you can see where it's emitting light at those wavelengths and where it's absorbing light. And this is an example from a northern hemisphere star, a Anova remnant. You can see on the left we've got some high energy excited atoms emitting light at these very specific wavelengths in the blue. These are mostly to do with hydrogen or helium. There's a big hydrogen one in the middle, which is usually the biggest, brightest one, and lots of stars. You can see that we've got an absorption line here where it's fainter. That's because we've got oxygen and it's absorbing light. So very excited, heated atoms will emit light at particular wavelengths of light. If it's a cool or low pressure gas, it will absorb light at particular wavelengths. The other important effect that we see in a spectrum like this is the Doppler shift, the Doppler Fizeau shift, as Renee reminded us last week in France. So that's where if an object is travelling towards you, the wavelengths get a bit kind of scrunched up and they get a bit bluer, and the whole thing moves to the left a bit. And if the object is moving away from you, the reverse thing happens and the whole thing moves to the right a little bit. So if you know where you're expecting to see a line and it's actually moved a bit to the right, you know that the object is moving away from you, and you can measure exactly how fast that is. So we use a spectrum to tell us some basic things about different kind of objects in the sky. That tells us about the atomic makeup of the object, what sorts of atoms and chemicals we've got in there. It tells us a bit about the temperature and pressure of the object, because if it's an excited atom emitting light, then we can work back and figure out just how excited and why. And it tells us something about the motion of that object along the line of sight. And one of the things that always amazes me about astronomy and astrophysics is that there's not actually much you can observe. You know, you can measure changing brightness of things, you can measure spectrums of things, and occasionally you can measure the shape of things, but not usually in stellar astrophysics. But from those quite simple observations, you build up this enormous body of knowledge about how the whole universe works, which astonishes me every time. So spectroscopy is a big part of modern astronomy and astrophysics. So, you know, the first big thing is classifying stars with different kinds of spectra. And here's the famous sort of Fibre classification. You can see we've got big lines in the blue on the left, and they change as you get to different kinds of stars. You've got big lines on the right. Again, that structure changes and you get different sorts of absorption going on. You can characterize the chemical composition of stars. You can look at temperatures and evolution. You can look at binary stars. Binary stars are rotating around each other. You can measure their motion with a spectrum and deduce things about that star system. You can look at the way that stars pulsate as they breathe in and out, and that's motion. You can measure it with a spectrum. You can look at motion within galaxies. So when Vera Rubin discovered dark matter, or discovered that there should be dark matter, she did that by using spectra to look at galaxies and look at how fast they were moving and compare that with how fast theory said they should be moving, or rotating at least. And of course you can look at galactic movement, and you can look at exoplanets, which you can detect with radial velocity measurements. Again, it's all about the motion of the star that's caused by the planet rotating around it. So there's a lot of stuff, a lot of science that's absolutely dependent upon the technique of spectroscopy. So a quick look at how these things work. This is a very simple abstracted kind of version of a spectrograph. You usually have a slit on the left, and you only let the light from the star you're interested in pass through that slit. So here's your star image. You put that through a lens, which gives you a nice parallel beam of light. You put that through your prism, or reflected off a grating, however you're going to make your rainbow. You put that through another lens, which rather confusingly is conventionally called a camera, and that focuses your spectrum onto your detector, your CCD camera or CMOS camera. And that's pretty much how spectrographs work. There are lots and lots of variants on how you actually do that, but conceptually they largely boil back to that. Having more detail in your spectrum depends upon having a larger prism and grating, and having a bigger telescope generally drives you towards having a larger prism or grating. So if you've got a 3 or 4 meter telescope, building a spectrograph for it is a big deal. It's a massive, expensive piece of equipment. If you've got a 10-inch telescope, on the other hand, actually your spectrograph can be quite small and therefore relatively cheap, and this is a good thing. it's important to be aware that spectrographs and telescopes have to be quite optically matched. You can't stick any old spectrograph on the back of any old telescope. So these are a few examples of some of the equipment that's now commercially available. Over the past sort of 10, 12 years, there have been two manufacturers, one in Germany, Bada, and one in France called Cheliac, who've started producing spectrographs specifically built for amateurs to use with small telescopes. These are very efficient pieces of equipment that are carefully optimized to work with the typical sorts of telescopes that you see people do astrophotography with, or photometry or other sorts of amateur astronomy. So this is a low resolution spectrograph. You can see it's physically quite small. It's only, this is the actual spectrograph unit here, this middle part. It's only about 5 centimeters long. It's much smaller than the camera that's bolted on the back of it. And it has a guiding module here and a guiding camera. This is quite important if you're actually doing it for real, because you've got your little slit. You're trying to get the light of the star through that and into your spectrograph, and you might have an exposure of half an hour or an hour. So you really need to be able to guide your setup so you can have really accurate placing of that star on the slit. This is a low resolution instrument. Technically, the resolution is 600, so it doesn't give you great detail about what happens in a spectrum. It's really intended for faint objects, and it can look at lots of quite faint things, and I'll give you some examples of that later. It's designed for relatively fast telescopes. This is just a diagram of that guiding setup. You've got light coming in from your telescope. This is the slit I was talking about, a piece of metal with a slit in it, which is actually at an angle. The light of your interesting star goes through to your spectrograph. The light of the other stars will reflect off the front of the slit and go into your guiding camera. So that's a bit like an offset guider, essentially. And it is really a vital prerequisite for doing spectroscopy with this kind of equipment. This is a much higher resolution spectrograph, but again, it's not physically big. You can see it's hanging off the back of I think probably a 10-inch Cassegrain or something there. It's only about 20 centimeters long. This is also made by Cheliac, French people. It's a little bit prone to mechanical flexure, but it's extremely powerful. It's got lots of different gratings, different slits, so you can look at different resolutions, and it's really intended just to use on your standard sort of celestron telescopes. This is a spectrograph I've taken of a Mira star using one of these instruments on a 12-inch. This is a very detailed spectrum. These are the two lines quite close together of sodium that you see in a lot of stars. All of this looks like noise, but these are actually real features of the star that are persistent from frame to frame. So there's a lot of detailed information in this image, which took, I think, about an hour. That's quite a faint star, that one.
Excuse me, Tom. Although we tested it earlier, your mouse doesn't seem to be showing up from what I can see.
Oh, okay. How's that?
Yes, that's better.
Okay, there are two screens here, so it's a thing. This is another one from Cheliac. This is a shell spectrograph, so it uses a fibre optic to carry light from the telescope to the instrument, so you avoid mechanical flexure. In this case, the spectrograph is inside a wine fridge. It's one of the French ones, to help keep it at a constant temperature. So this is somewhat lower resolution, but it allows you to look at the whole visible spectrum in one go, which is an enormously powerful thing to be able to do. So those are some of the sorts of things that are around. And actually, what's also important is that there's lots of other stuff too. So better mounts than we might have had in the past, auto guiding, the kind of cheap detectors that we have now, which are quite affordable compared to the way they used to be, and importantly, software and high quality optics. All of these things mean that it's much more possible to do this now on a moderate budget than it would have been 10 or 20 years ago. So it's challenging, but it's not more difficult than lots of other things people do. And I'll just quickly mention also that spectroscopy doesn't always require perfect skies. The optical designer of those French instruments, Christian Wheel, lives less than a kilometre from the Eiffel Tower, And he takes his 11-inch up to the roof of his apartment and does all sorts of very good things, what is quite an amazing achievement. So I'll quickly canter through some results showing the sorts of things that people are able to do with this sort of equipment. So this is a rather amazing guy in the UK, Robin Leadbeater. When you've got a nova or a supernova, then you need a spectrum to classify it. And you'll find a nova or supernova every week or two. The Assassin project throws them out with great regularity. You don't need very high resolution to do this, but they're quite faint objects. So this guy is using his 11-inch telescope, one of those low-resolution instruments I showed you before. He's actually modified it to give even lower resolution, which means he can go a bit fainter. He can classify nova spectra down to fainter than 17th magnitude, which is extraordinary with an 11-inch telescope. This is an example of the kind of thing he has. This is a raw spectrum up here on the left. This is the actual spectrum here. This is the raw image. This is all light pollution. You can subtract a lot of that light pollution and look at the spectrum here. And even just with the naked eye, looking at it, you can see that there are big, broad lines of brightness there. So the big, broad lines of emitting hydrogen going on. And you can do the graph of that. And that's enough to be able to classify it as, in this case, a type 1a supernova. So that's pretty useful stuff to be able to do. This is one of the French guys, Oliviers, who classifies planetary nebula. Same kind of thing. You don't need massively high resolution, but these are quite faint objects. People are finding planetary nebula candidates all the time, but they're mostly a tiny little splodge. It could be just about anything. So you need a spectrum to decide whether it really is a planetary nebula or whether it's something else. This is the kind of spectrum you get. So it's a very characteristic one. You get these lines of ionized hydrogen here, really bright, and hydrogen, ionized oxygen and hydrogen. And then these lines here, which are nitrogen and also oxygen. And they have this distinctive pattern, the three bright lines a bit further apart and the three bright lines together at the other end. This is some of Olivier's results. And actually, these top two have the distinctive pattern. They're very easily confirmed. But sometimes you find things that aren't planetary nebula, like these two in the bottom. One of these, I forget which one it is actually, is an active galactic nucleus. One of them, no one's quite sure what it is. So again, really useful stuff that you can do to support observations in science. Christian Will, the designer I mentioned, has some very high precision measurements of exoplanets. This is 51 Pegasi. He's getting a precision of about 100 meters per second in his measurements of the speed of that, or the wobbling of that star as a planet moves around it, which is pretty impressive. BE stars. This is a big thing for spectroscopy for amateurs. So they're young hot stars. They emit light and hydrogen lines. They're usually rotating really quickly, and they often have a disk. And there's still a lot of debate about how they work. But their features change quite quickly. And you can see here, most of the bright stars in Matariki are in fact BE stars. This is something which was a collaborative project between a number of professional and amateur astronomers in France. They set up a database to store spectra of BE stars because you really want to monitor them because they change so quickly. So this is an example that's got nearly 250,000 spectra in it now, that database, over the past decade or so. Which really supports the study of this kind of star. This is the hydrogen alpha line of one of the Matariki stars. In fact, in Matariki itself, you can see at the top here, we've got this double peak, which is a strong suggestion that there's a disk around that star. This is one of my own, a nova, again, a classification one, taken a day after discovery, just because it happened to be clear here on the right day. It's an assassin object. You can see huge lines of hydrogen there emitting really brightly. You can see from the width of those lines how fast the gas around that nova is expanding. And again, that allows you to classify the star. And I'll finish off quickly. Binary stars is a really interesting area for this and a classic area for using spectroscopic observations. So you can see on the left, we've got two blended lines, and one star, which is moving away from us at that point, has been blue shifted a little bit, and the other star has been red shifted a little bit. And they're overlapping, but in this spectrum you can distinguish the two, and this person has fitted lines to their two stars. So from that you can work back and deduce, you can see how fast they're moving, and you can deduce things about that system. On the right we've got some data here from the Puppis, which is the star I'm working on at the moment with Ed Budding. Same deal at the top here. These lines are from two different stars. In this case the star's rotating really quickly, so they're very broadened and they're a bit harder to measure. But we fitted curves to those and measured how fast the star is, or the two stars are moving, and we've managed to plot how quickly those two stars move in this graph you see here. This is the phase of the, sorry, I beg your pardon, this is the phase of the orbit, and this is how fast each of the two stars, the primary and secondary, is moving. Some of the data in this graph were taken at Mount John on the 1 metre, but some of them were also taken on my 12-inch at home. When you've got an object like this with such big broadened lines, you don't actually need massive precision. In fact, it's kind of overkill. So we've got results here that are very nearly as precise and useful of a really quite small setup. So there's a lot you can do. I think there's huge potential for interesting work. I think amateurs with typical sorts of setups in terms of your mounts and your telescopes, there's lots of scope for original interesting observations, which are tied to really interesting science. And the other thing is there's not many people doing this stuff. So there are quite a few in France and Germany. It's starting to attract interest in the United States. The AAVSO is running a spectroscopy workshop next week, but that's their first spectroscopy workshop. This is quite a new thing in the US. And in the Southern Hemisphere, there are literally a handful of people, a couple in New Zealand, about 4 or 5 in Australia. As a reflection, doing this really makes you engage with the science. If you're going to do spectroscopic observations, you really that really helps you to think about what you're doing, talk to other people who are going to use your data or work with you around the data, and engage with the underlying astronomy and astrophysics. And that's a very rewarding thing. There are networks of people out there to join and work with, which is enormously helpful, particularly the French networks, who are very welcoming. And there is software available to help with the analysis. And I haven't really talked about the software, but that is a big part of the exercise. And I guess as a final reflection, it seems to me that amateur spectroscopy today is a little bit like photometry was in the 1970s. As a wave of new equipment became available and accessible to people with small telescopes, but telescopes that are quite common and accessible, then you got a whole wave of new observations which supported some really interesting science. And I think, in a sense, this sort of equipment and activity is kind of poised to do the same sort of thing over the next decade or two. So that was a quick canter through some experience and observation and some results. We'll probably take questions.
Okay, thanks very much, Tom. Yeah, fascinating to see the possibilities that people can do in that area with relatively modest telescopes. Over to you, Steve. Are there any questions in the chat for either Tom or Nick?
Well, I've got no questions at the minute. If there are any questions, please get them in quickly. I've got a question though, actually. How did you get into amateur spectroscopy? What was the pathway in?
I was messing around on websites and just found it, really. I have to say, and thought I hadn't realised you could do that. This must be new, which it is. I did go to a workshop in the States about 1.5 years ago, before I started buying equipment and making observations, which was very useful. And I guess the other thing that's really important is the French networks. There's a forum in particular, which is very active. They're posted there every day, which both will provide technical advice, but also people share results, publications, and lots of activity, which is very, very helpful.
I think thanks for that. And we do have a question from the chat, again from Hamish, who asked the last question, who says, perhaps a short praise star analyzer transmission grating for beginning.
Yes, Hamish. Hi, Hamish. Hamish is one of the 3 people I'm aware of in New Zealand, counting me doing some of this at the moment. Hamish uses a star analyzer, which is really just a diffraction grating. You can get one for about $200, I think, from the French people at Cheliac. You can put that over your detector and do what's known as slitless spectroscopy, which is a much and get quite low resolution images, but still useful. And Hamish has got some quite good results of several objects, including Anova, doing that. And you really don't need very much equipment at all.
Yeah, I've got one more question that's actually from Dr. Nick Rattenbury, who presented previously, which is, can you estimate the cost of the spectroscope that you're using?
It's about $5,000. So not super cheap, but you can do a lot with it, and they last a long time.
Another question. Actually, the question's flowing here. So this is John Drummond. What software do you use to analyze your images? I use RSpec when I use my Star Analyzer 100.
Yeah, I use ISIS, which is a rather unfashionable name, but it's been there for a while, which was written by Christian Bouille, the French optical designer. I also use VSpec, which is written by the partner of Christian Bouille, Valérie Denou, for some aspects of the analysis as well.
Okay, and I think that's it for the questions. No more on the comment from Steve Butler that says, well done, Tom. I look forward to hearing more from you, and it would make a great article for Southern Stars.
Yes, here. Okay, if there's no more questions, we'll wrap it up there. And once again, I'd just like to express our thanks to both Nick and Tom for their presentations tonight, and remind everybody that there'll be another online session next Tuesday starting at 7:30, and hopefully you can join us then. So with that, it's good night.
Thank you, Glenn.
Thank you.
Glenn.